we're going to do an example of applying the Otto cycle. This is the kind of stuff that you do for your homework. I got an example. I chose something and worked something that's in the English units because your book has something that was in the metrics. So I thought it'd be something different. It's a little bit different in an example, but all of these are fairly similar in nature. Okay, how we do them. Okay, so let me start before I get into this. Let's just draw. You don't have to redraw this if if you want to, fine. But I want to draw this cycle again. Okay, state 1, we have the compression. State 2, the heat in. State 3, and then we got this here to state 4, and this back down. Okay, here's our PV diagram. Now let's read the problem. The temperature at the beginning of the compression process. Okay, well that's state 1, right? That's before we compress. Of an air standard Otto cycle. What's air standard mean? It means use the assumptions that we started with a compression ratio of 8, okay, is 540 Rankine. Okay, so the first thing we got is we know something about state 1. State 1 has a temperature, T1, of 540 Rankine. Okay, got it. Oh, and we know the pressure too. The pressure is 1 atmosphere. Now, we don't usually use 1 atmosphere that much, but that's basically the same thing as what's PSI of normal atmospheric pressure? 14.7. Yeah, let's do that. 14.7 PSI. So there's your temperature and standard pressure, okay? And 540 Rankine, that's not crazy hot, right? That's like room temperature, right? I mean, maybe a little warmer, but whatever, right? Okay. And there's the pressure. Okay, and a cylinder volume. Okay, so your cylinder volume is basically your max cylinder volume is 0.02 feet cubed. Okay, so there you go. Now, compression ratio. Compression ratio, R, is equal to 8, and that's equal to your max volume divided by your min volume, right? Okay. How else can I express that volume in terms of states 1, 2, 3, and 4? Volume 1, which is the max volume, divided by, what would be a min volume? Yeah, how about these are my max volumes here. And these are my mins. So volume 1 divided by volume 2. What's another relationship I can make between those volumes? What else has the max volume and this min volume? Yeah, V4 over V3, right? Yeah. So I can say in either case, compression ratio is V1 over V2 or V4 over V3. Okay, now, I haven't even got to what we're asked for. It says determine 3 things. The temperature and pressure at each state, okay? So I only have right now the temperature and pressure of state 1. That was given to me, okay? The thermal efficiency and the mean effective pressure. All right, so the first thing I've got to do is I've got to get the temperature and pressure of each state, all right? Now, I'm also going to do one more thing because I know I need it. And you don't know you need it right now, but I'm going to tell you that as we go through this problem, you're also going to need to get your internal energies of every state, okay? And as we go through this type of analysis, you're going to find one particular table to be very important, okay? And that's your air table, okay? So if you brought your tables, I would suggest you open them up, okay? Or I'll, you know what, I'll just bring mine up here. Let's go to our thermo tables, okay? And let's go, I think it's 17E, I recall. But I could be wrong. Here we go. Here we go. Ideal gas properties of air. When you do Otto cycle problems, you almost want to keep your finger on this table at all times, okay? Because you're going to use this a lot, all right? So the first thing we're given is a temperature of 540 Rankine. So I know you don't know this, but you're going to need this value. You're going to need 92.04. Let's write that down. 92.04 is the internal energy at state 1, okay? Okay, got that. U1, 92.04, and that's BTU per pound mass. Okay. Now let's go to state 2. That's pretty much everything we need to know about state 1. State 2, I want to find the temperature T2 and the pressure P2. Okay? What we're going to be doing here is we're going to, from 1 to 2, you do an isentropic compression, right? You're doing an isentropic compression. Everybody see that? What do you think is going to happen to temperature when you compress air? It's going to go up or down? Up, right? What do you think is going to happen to the pressure of air? Up or down? Up. Yeah, they're both going to go up. Temperature and pressure are going to go up. Okay? So how do we figure out how to get those? Okay? What's that? Ideal gas. We always, when do we ever not use ideal gas? Okay. That is very much the case. But let me tell you this. Ideal gas is going to be really helpful for us, but you cannot solve for both temperature and pressure with ideal gas. Try it. It won't work. Ideal gas is only one equation. How could you solve for two things from one equation? You can't. So I'm going to need something else. I'm going to need ideal gas, but I'm also going to need something else to do that. And the key thing is to recognize isentropic. Okay? We have, from 1 to 2, that's an isentropic process. That's an isentropic process. Now, you go back to your stuff, way back when, you're going to find all sorts of different isentropic relationship equations. Okay? The one that we're most likely going to use here is the following. We're going to write this. We're going to say the reduced specific volume at 1 divided by the reduced specific volume at 2, or relative, is equal to V1, the actual volume or specific volume, divided by V2. Okay? Now, you may have been like, oh, okay, I sort of kind of remember this, but I sort of kind of don't remember this. That's okay. You'll get used to it really quick. I do think you remember, I hope you do, that when we look up these tables, do you remember when we looked up this VR stuff and this PR? Remember that? We looked at this, we used this before with some relationships maybe a few weeks ago, okay? So we're going to do it again, all right? Now remember, VR and PR are dimensionless. They're not real volumes and pressures. They're dimensionless. But let's do this.
The ones that are in the gas.
Yeah, the gas tables. The ones that frustrate students because they go, oh yeah, it's, you know, they there's no units. Yeah, what is it? I don't understand. What we only use it for is a ratio. We only use it in the context of a ratio like that. That's how we use it. Okay? So that's why it doesn't have any units. Okay? Here's the deal. Here's what you can do. What do I want to solve for here? I actually want to solve for VR2. So I'm going to redo this equation. VR2, okay, is equal to VR1 times V2 over V1. Okay? Now, what's V2 over V1? What's V1 over V2? 8. So what's V2 over V1? 1 over 8, yeah. And what's VR1? Anybody have an idea how to find VR1? I've highlighted it. All right? You use 540 Rankine, and you got the VR1 there as 144.32. So what you do is you write this. You go, oh, well, this is 144.32 times 1/8. Oh, well, that's not bad. I can do that. And you get 18.04. Okay, so what do I do with that? You go back to the table, right? Yeah. Exactly. You got it. No, it's never right on the table, right? No, never. This time, it's pretty darn, 18.51 is kind of close to 18.04, sort of. And that corresponds to 1,200 Rankine.
12, 20 Rankine,
So
like halfway between 20 and 40.
if you interpolate it, okay, if you interpolate it, you get a temperature. If you interpolate it, you will get a temperature of about 1212 Rankine.
And then you use the ideal gas laws to find pressure.
You got it. See, this is awesome. You guys are good. I used to think that the morning class was my better class, but sometimes I think it's the afternoon class is my better class. I don't know.
Sometimes because I know this stuff and other times I realize I have no idea what's going on.
But you're getting it. Good. Yeah. So now we got the pressure. So we go, okay, well, let's use ideal gas law now to get P2. Now, remember when I'm talking about ideal gas. Ideal gas, you can pretty much, as long as the mass is constant, and in this case, we are having constant mass because it's a closed system, right? Okay. You can write this. PV over T. So if you have P1 V1 over T1 is going to equal P2 V2 over T2. Okay? And what I can do is I can take that ideal gas that I just wrote and rearrange it. I can solve for P2. It's going to be equal to P1 times T2 over T1, okay, times V1 over V2. And if you work this out, the pressure is good old 14.7 psi. My T2 over T1, well, I just solved for T2, it's 1212. My T1 was 540. And my V1 over V2, that's my compression ratio. Well, that's 8. And so now I just plug all that into my handy-dandy calculator, and I can get my PSI of state 2. So let me do that, since I don't have that in front of me. I think you get about 264 psi. Good, thank you for confirming. So the result for state 2 is 264 psi. Okay. All right, good. Now state 3. We know the temperature and pressure of state 1 and 2. Now we go to 3. We need to get the temperature of state 3 and the pressure of state 3. Yeah. This is yeah, exactly. Now let's go back to the original problem. I kind of skipped over this. It says here the maximum temperature during the cycle is 3600 Rankine. Where would the maximum temperature occur in this cycle? At state 3. Think about it. When you go from 1 to 2, you're compressing. That's going to heat it up, right? When you go to 2 to 3, you're adding even more heat. Well, that's going to heat it up even more. You're going to have your hottest at 3. Well, how about 3 to 4? Well, then you're expanding, so it's cooling off. So, and then 4 to 1, you lose even more heat, and you get back to 1. So your hottest temperature is going to be at state 3. Therefore, if it says maximum temperature in the cycle is 3600 Rankine, voila, that's really what it's saying is temperature at state 3. Okay, so how do we do P3? Hey, that's always good, yeah. If we do it air, and I'm never going to be mad at you if you just say ideal gas. Just, even if it's not the right answer, just, I'll be happy. Not that, I'll correct you or whatever, but I'll say, yeah, you can use ideal. But this case you do, yeah. Because remember what's 2 to 3? What's 2 to 3? What do we know between 2 and 3? It's a heat in. We don't know how much heat in, but it's a constant volume, not constant pressure, right? Constant volume.
Oh, yeah.
Yeah, constant. V is, constant volume. Yeah, constant volume. So remember what I have here in blue there? P1 V1 over T1 is equal to P2 V2 over T2. Well, simply wipe out the v's because they're constant, right? All you have to do between 2 and 3 is write this, right? You can just say P2 over T2 is equal to P3 over T3, right? Because the v's are constant. You can cancel them out, right? So if you want to solve for P3, well, that's rather trivial. P3 is equal to P2 times T3 over T2. Okay. My pressure at 2 is already given to me, or I solved for it, is 264 psi. Okay. So now my temperature, I've got all that. 3600 Rankine is my T3. My T2, I solved for it. It was 1212 Rankine. So then I throw all that into my calculator. 264 times 100. Well, I get 784, something like that, about 784 psi. It's a lot of pressure. Yeah. That's why we don't mess around when we machine out our cylinders, and you get those people that make those engine blocks. They're not going to be like, making them out of some, tiny little material and very hollow. And no, it's got to be pretty solid because we're having a lot of pressure inside.
Is
Yeah,
it like this right here? Is this like an accurate example of?
Yeah, it's not too bad. Yeah, I mean, it's not. It's anything like this, we're going to be off by some 20%. It's not crazy to be off 50, but at least it's in the order of magnitudes. Okay, it's not going to be like 70 psi. It's not going to be 7,000 psi. It's going to be in that range. So yeah.
Well, I mean, like all these initial pressures and stuff, and the max pressures, like these are kind of accurate for an average.
Yeah, they're not. We're not crazy far. Let's put it that way. Yeah, I mean, every engine's different. I mean, it depends on what we're talking about. The average engine. Yeah.
So like hemispherical engines,
Yeah.
they basically haul out off that piston or the bottom of the piston.
Yeah, gives you a little more volume.
That's all it's doing.
Yeah, that's all it is. Yeah, there's not much to it.
Sorry, the shape of it.
Yeah, that's just a little thing to give you a little more volume, because if you do that, you can change the piston shape and give you a little more volume. That's all. It's kind of gimmicky. Okay. So lastly, 4. Okay. Well, going from 3 to 4 is going to be a lot like going from 1 to 2. Okay? Because what you did from 1 to 2, you had the compression. Now you're going from 3 to 4, you've got the expansion. You've got the power stroke. Okay? So how am I going to get T4? I'm going to get T4 a lot like the way I got T2. Okay? So I need to get T4, and I need to get P4. Okay? So I'm going to get the temperature at 4 a whole lot like what I did before. I'm going to use that same isentropic relationship here. Okay? And so what I can do here is I can say VR3 over VR4 is equal to V3 over V4. Okay? And, oh, by the way, I do have to go back and get state 3. I have to look up its VR3. I have to look up that in the book. And if you go back to your table, state 3, by the way, is 3600 Rankine. So, hey, that's nice. That's in our thing here. If you look at it, here it is. VR3 is 0.6449. 0.6449 is VR3. So, state 3, VR3, it's 0.6449. Therefore, VR4 is equal to VR3 times, if you work this out, it's V4 over V3, okay, which is also 8, all right? And so what you have here is 0.6449 times 8, which is easily solvable to about 5.16. So then you got to go back to your tables, and of course it's never going to be 5.16, never going to be on the table.
Never.
Never. So it's going to be right in between these two values, And it's going to be somewhere between 1850 and 1900 Rankine, right in between these two. And if you interpolate this thing out, you will get about 1878 Rankine. 1878 Rankine. Then what you're going to do, just like we did before, we're going to apply ideal gas. Okay. And between, it's actually easier if you go between 1 and 4, it's simpler. Instead of going ideal gas between 3 and 4, which, by the way, you could do, you can actually apply ideal gas between 1 and 4 because that's a constant volume process. So we apply ideal gas between 1 and 4, okay? Then you can write the following. P4 is equal to P1 times T4 over T1, just like what we've done before. And P1, that's just 14.7 psi. Again, that's the initial pressure. Now we've got the temperature. T4 is 1878 Rankine, and T1, of course, is 540 Rankine, right? So you can put that in your calculator here. 1878, 40, and you get like 51.1 psi. Okay, so we got all our temperatures and pressures.
Yes.
Yeah, it's tedious. Yeah, takes a while to do one of these problems. When I give you homework next week, I can't give you a lot of these because it's just they take a while. And I have to give you less. Okay. Yeah. So yeah, I got to give you less. They just take long. I'm not going to give you 6 problems or anything like that. If I give you more problems, they're going to have to be not like this, you know. So, but these kind of problems take a while. Okay. Now, one more thing. You don't know this yet, but you really need to get the internal energies at each state. Okay? Let me just do this. I'm going to write them down for you here. We already noted that U1 is equal to 92.04 BTU per pound mass. By the way, how do we get internal energies? You look them up in the tables. All you need is the temperatures, right? All you need is the temperatures, and we solve for all the temperatures. You see that, right? I solve for temperatures T1, T2, T3, T4. So I got them all solved. So I got U1, that's that. U2 turns out to be 211.3 BTU per pound mass. U3, that's your highest temperature, so that's going to be your highest energy. And so that turns out to be 721.44 BTU per pound mass. Again, this is just from the tables. There's nothing special here. And finally, U4 is equal to 342.2 BTU per pound mass. Okay? Just use the temperatures, go to the tables, interpolate, yada, yada. Okay? All right, now, why do I need all this stuff? Well, in order to answer the last 2 questions, okay, I need this stuff. Okay? Last 2 questions. So we're almost home. 5 minutes left. Here we go. Last thing, efficiency. So part B, I got A, I got all my temperatures, all my pressures. Now I got to get my efficiency. All right? Remember, efficiency is what you get out, the work, the net work, divided by what I put in. In this case, it's Q in, basically fuel. Fuel equals heat. Right? Now, I can rewrite this thing, okay, because what I can do is I can say this is also 1 minus Q out divided by Q in. Okay, that's just straight up from your notes. Okay. Now, I'm going to help you here visualize this. I'm going to just one more time, just so that we see this real quick, draw this PV again. I know we've drawn it again, but I don't want to keep going back and forth to it. It's very simple. Here's 1, here's 2, here's 3, here's 4. One more time. All right, like that. Okay. Remember, where's the Q in? The Q in is here. Where's the Q out? The Q out is there. Okay? I put in heat between states 2 and 3. That's where I'm adding the heat. That's what the Otto cycle says. I get rid of heat between states 4 and 1. That's what the Otto cycle says. So, let me show you this. I can use my internal energies there. Because take a look at this. This is really 1 minus what represents Q out. Well, what represents Q out is the difference in internal energy between states 4 and states 1, right? Because why does state 4 and state 1 have different internal energies? Because of Q out, right? So the difference between the two gives me Q out.
So your efficiency between the three different states.
That would be, yeah, I guess so, but it can't really happen. Yeah, sure, sure, yeah. So this is U4 minus U1. Because that's what happens. The Q comes out of there. So that's U4 minus U1. And then same thing on the Q in. The reason why state 3 has more energy than state 2 is because we put heat in, basically the combustion process, right? So we put heat in. So that's U3 minus U2. So if you substitute your numbers in there, since you have all those numbers in there, boom, substitute them in. I'll just save you the math here and just go right to the chase. And there it is, 0.51 is your efficiency, or 51%.
So that's the maximum theoretical efficiency that could achieve.
No. That's a real efficiency of a idealized cycle. Yeah, it's idealized, but it's real. It's not maximum possible. Yeah. You could, by the way, twist the problem and say, what's the maximum possible efficiency of a heat engine? I'm not done. I got one. Stay with me. I got the MEP. We got to do MEP. You could twist this problem and say, what's the maximum theoretical efficiency? It would be the two temperatures, 3600 Rankine and 540 Rankine. Put those into your heat engine equation and find out what the maximum theoretical efficiency is. Okay, lastly. Yeah, it's not horrible, but it's not spectacularly out of range, but it's pretty good. Yeah, that's good. That's
quite high.
Yeah, it is. So, yeah, well, we might be able to get 35%. That's not too crazy. So, maybe 40. Okay, C, MEP. Now the MEP, again, is your net work divided by your volume max minus your volume min. Okay. Your net work, there's two things that make up net work. Okay? Let me show them to you here visually with this on this chart. There's your power stroke. Okay? So what represents the power stroke? Well, that would be U3 minus U4. That's the work you get out, right? Because U3 has way more internal energy than U4. That's what you're getting out of this engine. Okay? But that's not everything, because the net work is the power stroke minus the compression stroke, because I have to put some, unfortunately, every time I run a cycle, I have to put some energy back into this thing. And so what you have to do, really, your network, is U3 minus U4 minus U2 minus U1, because that is really your total net. And then, this is all on a per mass basis, but you can actually, given the cylinder volume, you could actually figure out the mass. And I'm going to go quick here to save you some time. But you can actually figure out the mass. And I'll show you that real quick here. Let me do the bottom. The bottom is very simple. The max volume of the cylinder is easy. That was given in the problem as 0.02 feet cubed. Your minimum volume of the cylinder is also easy. Because you know your compression ratio, it's 1/8 of 0.02 feet cubed, right? Because your compression ratio says your minimum volume is 1/8 of the size of the max volume, right? So the only thing you don't know here, you know U1, you know U2, U3, U4, everything. The only thing you don't know is the mass, but you can use ideal gas. Mass is equal to PV over RT. You can use ideal gas to solve for it. I'm going to spare you the details. You can do this on your own if you'd like. 1.47 times 10 to the minus 3 pound mass. By using that, good check for you. Do this on your own. Make sure you can get that for English units. Okay, English units are a little different, yeah. So make sure you know how to do that. And that gives you, if you plug this all in, it gives you an MEP of about 118 psi. You might say, well, what does that mean? It's basically, you don't really know what an MEP is on its own. You have to compare it with other engines and say, well, this one has this design, has an MEP of this one has this. And it's just a relative comparison. It's saying power divided by volume, so it's kind of giving you another measure of efficiency.
Is that a quarter stone?